In this section of chapter 10, we'll discuss about synthesis of esters, amides, anhydrides, nitriles, and their reactions. If you know mechanism of some of these well-known reactions, it would really help you. That way you don't need to really memorize each and every reaction. And most of these reactions you already had, because benzoyl chloride reaction with an alcohol, this is the well-known mechanism where electron pair, this is electron pair on oxygen, is attracted to carbon, this carbonyl carbon with delta plus. So this electron pair gets attracted to that carbon and it makes a bond. But this carbon with carbonyl oxygen would have too many bonds, so it has to break down its pi bond and release its electron onto oxygen. So you get something like this. In next step, it tries to get back its double bond by pushing out Cl, and Cl is a good leaving group. In other words, Cl leaves and it makes its double bond, and that's why you get this product. Again, this is another chloride, acetyl chloride. Acetyl chloride because CH3COOH is acetic acid and OH group is replaced by Cl, so that's acetyl chloride, and it reacts with acetate ion. This is an acetate ion. R could be any group. If you consider an alkyl group, I would have, say for example, CH3CH2. I can write down the simplest one, CH3 C double bond O minus. So this is O minus, and again O minus gets attracted to the carbonyl carbon, which has delta plus, so it gets attracted, and then the double bond would initially be broken like this. Then when it forms the double bond back, the chlorine gets out because otherwise carbon would have too many bonds, and chlorine is a good leaving group and that helps in this reaction. So finally you get anhydride. If you use your methyl here, R becomes methyl. So then you end up with this product. This is an anhydride having two carbonyl group and an oxygen in between. Here you can see a series of reactions given by anhydride. So this is anhydride, and you see it's reacting with H2O, alcohol. You can see that alcohol and H2O, actually the difference is one of the hydrogens of H2O is replaced by an alkyl group, and that's why you have R there. And it could be any group that I didn't write down any specific formula. In each case, there is a pair of electron. Like in case of nitrogen of ammonia has a pair of electrons. So it will be attracted to either of these two carbon. It's going to give identical products. So oxygen is delta minus. Let me show you a reaction with ammonia. I think then you can understand that how it works. R, C double bond O, O, C double bond O, then another R. Again, I said that R could be any group. It's not any specific group. It could be an alkyl group. And when ammonia, nitrogen with pair of electron goes in here, it could be either of these two carbon. Let me show you when it goes to this carbon. When it goes to that carbon, the double bond is going to be broken, and then when it tries to make the double bond, it pushes out this whole group, and you finally end up with this product. And NH3 would be initially plus, and then finally it releases H plus and becomes RCONH2. So if you know a little bit of mechanism, then that would really help you in predicting product of a reaction. Now, in presence of hydroxide ion, obviously this is acetic acid, or it could be one of those carboxylic acids, depending upon what Re is, becomes O minus because NaOH reacts with H plus, giving H2O. So you get this acetate ion. Now, acetate ion has pairs of electrons. So it'd be 1, 2, 3, 4, 5, 6. And those, any of this pair of electron will be attracted towards the carbon, which is delta plus. And as it makes a bond with the carbon, this carbon, shown with asterisk, it has to get rid of one of its bonds. Otherwise, it would have too many bonds. Since iodine is a good leaving group, so iodine leaves with electron pair, and you finally end up with a methyl group attached here. So where I'm showing you here, this is the R prime. That means this. In this case, if you are using methyl iodide, here you'd have methyl. In case of an alcohol, obviously alcohol gets bonded to this OH after release of water. And let me show you one such reaction, a specific reaction, CH3, CO, OH, and say I'm using ethyl alcohol, CH3, CH2, OH. What I'm saying is we can get rid of OH from here and hydrogen from here, and that would eliminate H2O, and then you'd get an ester with this formula, CH3, C double bond O, O, and then the bonding is here, CH2, CH3. So this is the final product. And that's ester, because this C double bond OO is an ester group. Thionyl chloride, just like in any reaction with alcohol, replaces OH of carboxylic acid by Cl. So if I have CH3, CO, OH, and if I use SOCl2, I end up with CH3, CO, Cl. So basically this OH would be replaced by a chlorine. Now here you see other reactions. You already know these reactions. Lithium aluminum hydride that releases H minus. So similarly it's going to work on this carbonyl carbon. This is delta plus, this is delta minus. So this is H minus is going to be attracted to this carbon, and it's a very similar reaction. Once you go through all the steps, you'd end up with CH2OH, or 1 degree alcohol. With ammonia, it gives amide, and with OH minus or H2O, it would give you C double bond OOH. So that's basically how it's going to work. If I show you just one step of the reaction, maybe that would be helpful. Let me show you reaction with OH minus. Say you forgot what product you're going to get. So let me write down R, C double bond O, O R prime. Again, these are alkyl groups. I didn't write down. R and R prime are the alkyl groups. I didn't write down specifically. So here you have delta plus, here you have delta minus. Now when you have OH minus, you have 2, 4, 6, that's OH minus. and it gets bonded here, and then electron is released there. And what you initially get is the following. If you follow all the arrows, C, O minus, O R prime, and then you had OH here. Now this would try to get back its double bond. So then R prime O would be leaving to make room for double bonded carbon, and as it leaves you end up with this compound. Again, this is a pretty much repetition of what we discussed before. Lithium aluminum hydride releases H minus, and it's showing you the mechanism how H minus reacts. Initially it forms something like this, and then as oxygen makes this double bond with carbon, carbon has to get rid of one of its bonds, and it gets rid of OR prime, and so that's how it gets aldehyde. Then an additional H minus reacts with aldehyde and finally end up with this, which in presence of an acid would give you 1 degree alcohol. Now Grignard reagent also acts in a very similar manner. You know that magnesium is plus, so basically C with minus charge gets attracted to this carbon with positive charge, and that's why there is an arrow going from carbon to that carbon. So this is how this ethyl group gets bonded, and then initially the double bond of carbonyl carbon oxygen bond would break down, and that's why oxygen gets negative charge, because oxygen gets that extra electron, and then it forms back the double bond. When it forms back the double bond, it releases OR prime that goes back to the solution, and you end up with this compound, which is ketone. Then another mole of ethyl magnesium bromide, which is Grignard reagent, is going to react with ketone just like before. This carbon with pair of electrons will be attracted to this carbon, and then it'll get rid of that weak pi bond and dump it onto oxygen, so oxygen gets minus. So what basically we get is the following: RCO minus, this is minus, and then CH2, CH3, and here also we have CH2, CH3. Now, unlike previous steps, this oxygen cannot make a double bond, because if it wants to make a double bond, let me show you that if it wants to make a double bond by making a carbon-oxygen double bond, one of these groups will have to leave, and these are alkyl groups, and they would not leave. They're not a very good leaving group. So in other words, this is not going to happen. So what is going to happen is this is going to pick up H plus. That's why in second step H3O plus is added. H3O plus is nothing but the water with an acid. So that H plus gets bonded, and you end up with this product, which is a tertiary alcohol. Now, from acid chloride, so this is acid chloride, you can get amides when you react with ammonia. Again, chlorine is a good leaving group, so that leaves. Or you can get some of the derivatives where nitrogen remains intact, but out of 2 hydrogens, 1 hydrogen will be replaced by one of those groups, and that makes it doesn't make any big difference in the reaction. It's very similar to reaction with ammonia. So that's what we're showing you here. Now, once we have amide, C double bond O NH2, that's the amide functional group. in presence of water or OH minus is going to give you carboxylic acid. Okay, again, we can predict this. If you think OH like this, 1, 2, 3, 4, 5, 6, this OH will be attracted to the carbon. Carbon breaks its double bond, releases it onto oxygen, and then let me show you that eventually it would like to get back its double bond. If something wants to leave, then NH2 leaves as NH3 because you have H plus added. So when H plus is added, NH2 becomes NH3. And NH3, any neutral molecule is a good living group. So it gets out and you finally end up with this product. Similarly, nitrile formation can happen from alkyl halide. Why we pick alkyl halide so often? Because halides are a good living group. So in this case, cyanide goes to this carbon, which is delta plus. And again, it's the same story. Carbon would have too many bonds, so it gets rid of the bond between carbon and bromine, and bromine leaves. It is a good living group and it's always eager to leave. In this slide, we are showing you a number of reactions given by nitrile or C triple bond N group. Like if you're using OH minus or H2O or H3O plus, it's the same thing that with electron pair. Let me show you. If you're using OH with 2, 4, 6, this oxygen would be attracted to this carbon because carbon has delta plus, nitrogen has delta minus. And as oxygen makes a bond, then carbon breaks its triple bond to double bond, and it becomes a double bond now. Nitrogen gets the negative charge, and eventually it is going to pick up hydrogen. So this is how this reaction proceeds. At least the first step of the reaction goes that way. And then if you keep on adding next time another OH, then eventually the nitrogen leaves as NH3, and that's how you get COOH. Instead of H2O, we can have lithium aluminum hydride, which releases H minus. So keep that in mind. H minus is also attracted to that carbon the same way the reaction would happen. So only difference is here nitrogen doesn't leave. Here even nitrogen remains as NH2. This is the Grignard reaction where R prime gets out as minus. So when you have R minus, that's attracted to the carbon, just like before. And first triple bond is broken to double bond, and then double bond becomes, in this case, triple bond would break into double bond, and eventually this nitrogen leaves and is replaced by double bonded oxygen, and that's ketone. Every step of the mechanism is not well known, but even if you can predict the first step, you'd have an idea what product you'd end up with. Here we're seeing the reaction given by Grignard reagent in more details. First you get formation of C double bond N, which eventually would get this compound, ketone, and ammonia is released. Here you see polymer formation, and this is very commonly applied. It's nylon, you heard about nylon, adipic acid, and hexamethylene diamine are used. And here we are showing you how these molecules get bonded by the release of H2O. Now in last slide, we're showing you formation of polyester. So basically here, again, it's the same polymer formation by combining different molecules together. your CH3OH is the group that gets out and it allows one molecule to get bonded to the other molecule and finally get polyester. That means you have lots of ester groups.